All right, we're back again. Here to talk some more about Cosworth Pi Toolbox and looking at PDR data with it. Today, what I want to talk about was math channels. Math channels are pretty cool because they allow you to get a lot more value out of your data than what's just raw displayed in the channel. So it allows you to take the data for channels and do things like look up external data sources and then use a set of functions, actually a pretty extensive set of functions, to go ahead and manipulate that data to create a new channel that then gives you new insight into what's happening. So, a couple of examples I've used before, and I'll just kind of show you what they look like right up front before we dive into how they do it is, I like taking the derivative of things because that basically gives you a way to see rate of change and not just a value. So an example of that would be, let's go ahead and take the brake sensor and plot it on a graph here. You'll see this is brake effort for a couple of sessions, but if you look, brake aggression is nothing more than the derivative of the brake. So how quickly am I going on the brake? How quickly am I coming off the brake? And if you plot that, you can kind of see just how quick your transitions are. So that's useful for figuring out your technique, right? Another one is steering. So I showed this in the tank slapper video. So we'll go ahead and let's take these out. Keep it nice and clean. And take steering speed. And here you can see we've got these big spikes. This basically means I had to do something quick to catch the car. So, right here we've got this huge spike in steering speed. So that's basically rate of change for steering angle. And if you go and look at yaw rate, you'll see there's also a lot of yaw rate going on. So this is me actually trying to catch the car here in a corner. But how do you set these up? So first thing they do is if you actually go into Tools, Pi Math, there's a couple of functions here. Edit is where you actually create and edit your math channels. There's also an import and export function. So you can take your math channels, either all of them or just select ones, export them to a file, so that way you can actually share them with other people, you can back them up. Pi math channels don't persist between workbooks. So if you're creating multiple workbooks, then you want to go ahead and export them and then import them into your new workbook. So let's go ahead and take a look at some of the ones I'm using. These are just the simple derivative ones I talk about. So accelerator speed, here we're using the function derivative. Channels are always in brackets. So just kind of some basics here. We'll go ahead and edit this. First of all, if I want to know what functions are available, control space will actually give me a drop down. So I can actually scroll down through all the functions and all the operators that Cosworth has put into the tool. And you've got math functions, you've got filters. Again, we'll talk about lookups here a little bit. But if I hover over it, it also gives me the usage. So, here, let's take derivative. Here it's just the channel I want to take the derivative of and discontinuity mode. So basically what happens if I've lost the data. So I tend to always just use reset. But in this case, this channel is just taking the derivative of the accelerator, and basically if it can't find the data, it just resets itself. So a couple things about math channels. Here where data rate, I tend to take off of the channel I'm actually operating on. So I want the same data rate as the accelerator in this case. When you create the math channel, you have the opportunity to define data types down here. This is probably not the best example because I don't have a real clean data type. Let's take calculated acceleration. So exact same idea. Acceleration is rate of change of speed over time. So we're just doing the derivative of speed to calculate acceleration as miles per hour per second. That's not a good example either, actually. Let's take gsums, actually, are a good one. So gsum, we've got, in this case, this isn't just a simple derivative function. Here we're doing something where we're taking the lateral acceleration channel and the longitudinal acceleration channel, and we're actually saying, what is the total number of g-force I'm inputting into the car? If you think of your friction circle, you've actually got only so much grip in the tires, and that grip can be used for braking, that grip can be used for acceleration, that grip can be used for cornering. And so g-sum is basically the sum of all those forces. So in theory, you can see how close you're getting to the absolute edge of the grip of the car. So here, fabs is a function. We just hover over it, we should get a pop-up that just returns the absolute value of something. So in this case, we're taking the absolute value of lateral acceleration, because normally that's either a positive or a negative depending on whether it's left or right. And we're taking the absolute value of longitudinal acceleration, which is also one of those positive or negative depending on the directionality. And we're adding them together to get basically a total value. And in this case, the data rate, I have it fixed at 50, but really I should probably have that the same as one of these channels, lateral acceleration or longitudinal acceleration. And then as far as data type, let's go ahead and change that to, oh boy, I think it's acceleration standard gravity. So that's actually what it should be for a G-sum. So here's an example where I'd slap the channel together and actually finish setting everything. And if I go ahead and hit apply, a couple interesting things happen. If you go ahead and close it out. If you go look over here in our channels list, you see where there's now this gsum.acceleration, whereas before it was called gsum. This is what happens when you create a channel with one unit and then you change it to another unit. It appends the new unit to the name. The only way to get rid of that I found is actually to go ahead and delete the channels, start over again, and then basically make sure you have your units set correctly in the beginning. But to show you what that gsum looks like, we'll go ahead and plot it out, and we'll take out our steering ones we were playing with before. And again, here you can see kind of the absolute lateral and longitudinal G's in total going into the car. So we've got a max of, if you look over here to the right, 1.79 G's. That's probably just a spike. One thing you could do by actually messing with the data rate is actually smooth that out a little bit. So that tends to miss some of the spikes, or you can apply a filter to it. So let's go ahead and actually do that. Let's go to Alt-3. Let's go to gsum acceleration. And let's actually apply a filter to it to try to smooth that channel out a little bit. So we're going to apply a bandpass filter. And then, oh, I actually don't want a bandpass filter. I want a moving average filter. Set that, go ahead and set the price. And so let's set that over a period. So let's say, 0.25 seconds. See what happens to my data. Well, here you get slightly different data, but not by much. So these are still pretty valid. Let's go ahead and change that a little bit. See if I can have peaks that are maybe a little bit longer. Let's do 0.5. And that actually brings down some of that spikiness of the session. So going back into our math channel editor, what else do I have in here? Well, a lot of derivative functions again. So damper velocity. So we've got with the 2017s and above, you've actually got suspension movement data. So by taking a derivative of that, I can see how fast is that shock moving, not just how much did it move. Distance toolbox we covered in our very first video. That's actually calculating distance from speed. I'll come back to this distance by lat long later. That's a really complicated one. But one of the ones I really thought was pretty cool, took me almost a day to figure out how to do this because the documentation was kind of lacking, was effective torque. You've seen me use this in a number of videos. And this is using an external lookup and a channel inside of Toolbox to create a new channel. So in this case, I want to know what the effective torque of the motor is based on the torque output that the ECU is telling me and the gear that it's in. So I have to have a lookup for that because I have to be able to multiply it times a gear, and I have to know what the gear is. So the good news is there's a channel for gear that gets output by the ECU. So that's this bracket gear right here. But I had to provide an external table to look it up. So in this case, what I'm doing is I'm giving it a spreadsheet. So let's go ahead and look at that spreadsheet real quick first. So my gear ratio spreadsheet is really pretty simple. Your left-hand column here, this is your index column. So basically, frankly, the titles don't matter. The kind of row here, row 1 here doesn't matter. That's just for me. And actually, row 9 here doesn't matter because there's no such index as final. But what Pi Toolbox is going to do is, as it sees a value in the A column, it's going to look for its corresponding value in the B column. So I'm basically taking the gear as an input, and depending on whether it is 1 through 7, I'm returning this ratio value that's in the B column. So if we go look back at our math channel, what we're doing here is the format's a little funny. So this pound gears basically means you've got a table lookup. So you've got a table keyword, hashtag or pound, the table name you want to give it. These are case sensitive variables, and table names or registers and table names are all case sensitive in Pi Toolbox. And then you're saying this is my path to it. So C data, C7Z06, gear ratios.xls. Then you append another backslash to it, and you give it the actual sheet name inside the Excel spreadsheet. So again, if you go back and look, I have sheet 1. I actually have 3 sheets in here, by the way. This one is for the manual transmission. Sheet 2 is actually for the, I believe that was for the, it's obviously for the 10-speed auto. They use for the ZL1, and there's the 8-speed auto that's in the Corvette. So sheet 1, and then an exclamation point, and then the row of cell, or the range of cells that have the values you want to get returned. So here we have B2 to B8, which corresponds in my spreadsheet to B2 to B8. So it's always going to take these, look for the index to the left, and that's what it's going to return. And then a semicolon at the end. When you get into more advanced math channels, you'll see that you need a semicolon at the end of it, except for when you're returning the value. So now when I call into that thing, I actually am doing 2 things in this next line. First of all, I'm saying, hashtag gears, so call the gears table with a parameter, so open paren, bracket gear, bracket, close paren, and that's going to return that value. So if I'm in 3rd gear, it's going to return 1.21. And it's going to take that value and multiply it by the current value of the engine torque request channel. So the other thing about math channels to remember is the last line is effectively your return value. That's what gets sent back and plotted on the graph. So here, I've basically defined the table, and then I've said, at the moment you're doing this math channel for that piece of data, go look it up, get your current gear, multiply it by the current torque request, and return that. So that's how the external lookups work. That's a really simple case. You can actually do multi-dimensional, where you can have basically different columns and rows you're looking up against. I've not had to do anything like that. The Cosworth documentation is okay in that respect, but it took me quite a bit to figure out how to do this correctly. A couple of tips if you're going to do this and you can't figure out what's going on. If you right-click on the link here and do verify table definition, it will actually go out, look at the spreadsheet, and basically say, can I access that? Does that look okay? And it will return okay. If I do something like set this to 0, actually clear this value, 0 is actually probably value, and save it, and I do a lookup, here it'll tell you invalid index row cell A4. So it's pretty helpful that way at telling you what's wrong with your actual lookup here. Now, what do we want to look at next? So we've done effective torque. Let's look at something that actually uses registers. So let's go ahead and take the watt time channel. So here's a channel I created because I was trying to figure out in a given lap, how much time was I full throttle? That's useful for knowing the number of seconds. You can also plot it as basically segment time. So actually, let me show you that first, and I'll come back and look at the channel. So if we look at, let's see, segments, and I want to add, let's say, to these tables, I want to add watt time. Oops, Alt-2 to get to the add watt time. And so I'm basically saying, give me the maximum time I've spent at watt. Maximum is the only thing that really makes sense here because it does increment, and then in each segment. So in this case, this is just my lap report. My apologies. So this is amount of time at watt for each lap. If I want to do segment reports, I actually have to look at the split tab here. So we'll do this over here as well. So Let's see, here I have elapsed time in my split reports. If I were to remove that and just add watt time, and then look at max, you can see that now I have per segment number of seconds at wide open throttle. I didn't change them all, but hopefully you get the idea here. So this is one of the interesting ways you can do split reports too. Split reports don't just have to be time in the sector. It can be amount of time in watt at the sector. It can be maximum, or minimum oil pressure during that sector. You've got a lot of options within these tables. But let's go back and look at the math channel and how I created it, because it's actually kind of neat. Tools, Pi Math, edit, watt times. So we're getting into some fairly tricky stuff here. The first thing is with math channels, you have something they call registers. They're like variables. If you write any code, they're kind of the same thing as a variable. And what you basically do is just use the register keyword. You put a ampersand in front of it, and then you give it a name. Again, the names are case sensitive. This here is the initial value. So this is only set at the beginning of the outing. So one thing that's important is unless you're changing something in your register, the registers will only reset at the beginning of the outing, not the beginning of the lap. So if you have an outing with 10 laps in it and you have something where you just increment the channel or increment the value of the register, it will go up lap after lap. So what we've done here is we've created one I call watt, one I call time, and now I want to actually reset that value at the beginning of each lap. So I've got a little bit of a hack that I put in to do this. So there's a choose function. So choose function is basically you take the first thing you put in, and officially if it's non-zero, it will return the second value or the third value in your parameter list. Otherwise, it will return the second value. So in this case, non-zero is basically true. So in this case, we've got, I'm going to say, let's say is elapsed time right here less than 1/10 of a second. So that basically means, is this the beginning of my lap? Because elapsed time for the lap is less than 1/10 of a second. If it is, return 0. If it's not, just return the watt value from before. So what I'm doing is I'm initializing time each time I run through this function to either what watt was before or to 0 if it was the beginning of the lap. So now what I do is I say, okay, is my accelerator, am I at full throttle? And I didn't do necessarily 100% because there's a little bit of play in the sensor, and 98% is effectively watt. You're not going to be able to modulate with your foot 2% of the pedal position. So again, I use a choose function, and I say if the accelerator is greater than 98%, then I'm going to take this time function that I just established, and I'm going to add 1/100th of a second to it because our cycle time is 100 hertz. And if not, we're just going to basically keep it at the value that it was before. So I'm incrementing this time value and returning it as watt if I'm at full throttle. And then I return watt. So this becomes what gets set. And so what happens is each time this function gets called, 100 times a second as it's plotting the data, it's going to go through and say, okay, is it the beginning of the lap? Yes or no? No. Okay, great. Let me go see. Are you full throttle? Yes. Then let me go ahead and increment that by 1/100th of a second. And so the result is you end up with a nice channel. We'll look at over here. Take that out again. It's basically a stair step. So you see where I'm full throttle during the lap. Okay, and you can see obviously it's going to correspond to the straights. But you don't tend to use this in a graph. Again, this is one of those things you would use either in your sector times, like I said, or your actual lap overviews. Now, let's say we want to do that as a percentage. We can go ahead and, Pi Math, edit. It's a really quick change to make this a percentage as opposed to pure time. All we do is at the end, we basically change it so we take the number of seconds at watt divide it by elapsed lap time. That gives us percentage, multiply it by 100. Hope everybody found this helpful. As always, please subscribe. If you have any things you'd like to see me talk about, please go ahead and post in the comments. Also post any questions you have there. I try to be pretty quick with responding to them. And track season is getting underway here. Pretty soon we'll be looking at some new fresh data. So again, thanks everybody and have a good one.